So say you started with the random variable x and you know this density function f of x. So we're going to come up with a general formula because I haven't given you a specific density function. I say supposing I knew f of x. Let y be x squared. What will the density function of y look like? So if y is x squared, find the probability density function of y. So let's follow the steps that I've written down there. If I had given you the values of x, this problem, you could write down more explicitly what values of y would be. But what do you know for sure? Y cannot take negative values. Okay, so you definitely know y is greater than or equal to 0. If you knew that x only took values up to, say, 5, then you know that y would take values up to 25. But for right now, all you know is that it's going to be non-negative. So you already know now some information that the density function is going to be the density function is going to be 0 when y is negative. Okay, so you already have some information. So step 2, let's write down the cumulative distribution function of y. So these are the steps you're going to follow for every problem. So cumulative distribution function. By definition, that's the probability that y is less than or equal to 1. What's our next step? We write it in terms of x. So this is just saying this is the probability that x squared is less than or equal to y. Now this looks a little similar to what we did in the discrete case. So what does this mean? This means that your random variable x can take values between this and this. So you could integrate from negative square root of y to plus square root of y, your density function for x. I mean, this is what this probability is.
We're supposed to have square root on the right side too.
Oh, yeah, yes. So you could do this, but since we're looking for a general formula, let me write this down as follows. This is nothing but, or in this, if you don't want to do calculus, is just your distribution function of x at the upper endpoint minus the distribution function of x at the lower endpoint. Okay. This was something that I mentioned earlier, that the probability that a is less than x is less than equal to b is nothing but the distribution function of b minus the distribution function of a. So that's what I'm using here. Now, it's good that we can write this in terms of the distribution function for x, because now when we differentiate this, we will get the density function of x. So let's differentiate. So if you differentiate, you get the density function of y is just the derivative of this. So this is just this, so we need to differentiate this with respect to y. So what is the derivative of this with respect to y? You basically use your chain rule, right? So you have the distribution function of x, when you differentiate that, you get the density function of x at this point, times the derivative of the inner function, which is 1/2 square y here. And then minus, you get your density function of x times the derivative of this, that's negative 1/2 square root of y. So this gives you can just factor that out, like this. So you see that if you're given any random variable x and you're asked to find the density function of the square of x, if you want to just memorize this formula, you know you can always use this. So this is what a density function of the square root of the square of x will look like. It's just going to be, it's like take the average of the density function at square root of y and a negative square root of y and divide by square root of y. So if you want, you can plug in the density function for any of your known distributions. Say you can take x to be uniform, you can take it to be normal, you can take it to be exponential, and you will see that the distribution of x squared is just given by that. All right, so let's go over this again. So you do this in 3 steps. You don't find the density function directly. You first find the cumulative distribution function. First step is determine values of y. Oh, so to be precise, you know that it's going to be this when y is greater than or equal to 0, and 0 if y is less than. Oh, strictly less than 0. So that's step 1 is important. All right, and then step 2, you find your cumulative distribution function, then write in terms of x, and then step 3, just differentiate to get your density function. All right, so let's do this for a few more examples of this. All right, so here's an example where well, now we have a general formula. You could just use this, but I would suggest that you try and derive this. Square of an exponential. So let x be an exponential random variable with parameter lambda. That is, your density function of x is lambda e to the negative lambda x. 0, 0. Find probability density function of y equals x. So what I'd like you to do, basically, as I said, we just proved a general formula for the square of any random variable. So essentially, you should end up with this formula, where you've actually plugged in the density function for your exponential random variable. But don't use that formula directly. Try and derive it step by step. So the first thing you do, what are the possible values your random variable y can take? It's x squared, and also if an x just takes values equal to 0. So step 1, y takes all values greater than or equal to 0. Step 2, start by writing down the cumulative distribution function of y. Basically, you're going to just follow everything in this. In this. But when you come here, or you can use this, you would actually have to plug in the correct formula of that. So you'll have to see how this changes. Because, okay, so there is a subtle difference here. Here I'm integrating from negative square root of y to plus square root of y, right? Well, okay, do this problem, and when you get there, tell me what happens.
was that third step? Take derivative of.
Of the distribution function. So let's do this. Step 1. Y takes values of y greater than 0. Step 2. Let's calculate the cumulative distribution function of y. It's just the probability that y is less than or equal to little y. So the probability x squared is less than or equal to little y. This is the probability that this. Can x take values, can it take negative values? No, it can't. Oh yeah, so at this point maybe to be technically correct you need to say take. You're only interested in values of y that are greater than or equal to 0, right? Because your random variable doesn't take any values less than that. So take y greater than or equal to 0. Because also you see y has to be greater than or equal to 0 because otherwise you couldn't take square root. Alright, if you look at this, x does not take negative values because your random variable x is exponentially distributed, right? So this just becomes a probability that, or it's just the integral from, instead of negative square root of y to plus square root of y, it's just given 0 to square root of y. Because from negative square root of y to 0, it's just 0 to integrate. So here you have lambda equal negative lambda x dx. When you integrate this out, if you remember your distribution function, you know that this one 1 minus e to a negative lambda square root. So this is essentially just right, and that's 1 minus e to negative lambda square root. So what do we know now? We know that your distribution function of y is given by this. So to get the density function, we know the distribution function is the integral of the density function. So the density function of y is obtained by just differentiating this. But this is just this function, so you're just differentiating this. So you get negative e to the negative lambda square root of y, negative lambda. So you get lambda to the square root of y, and negative lambda. And now we can check, do we get the same thing as we expect to get because we have a general formula? You see that we do because here fx of negative square root of y, f of a negative value is 0 for exponential distribution, so that is 0. So you just have this divided by 2 square root of y. All right. All right, so let's do another problem where we have a different function.